Hi everyone. My name is Qing and I'm your IDL TA. And just now Vadan introduced to us about deep Q learning, which is one of the state of art for deep reinforcement learning. And now we are going to explore in another areas of popular deep reinforcement learning method, which is policy optimization. And specifically, we explore into PPO in detail. So firstly, what is policy optimization? To understand that, first of all, we need to know what is a policy. So a policy is a function pi that maps a state S to actions A. And so implicitly in a value-based method, like deep Q learning or normal Q learning or double Q learning, there's no explicit function for the policy. What we are doing is basically using the greedy method, and at each state we are taking the argmax of action that maximize the Q value. However, as we have often learned, that the greedy method might not be the optimal method always. So now we are going to look at policy optimization. So in value-based methods, we learn a value function, and the idea is that an optimal value function leads to an optimal policy. However, in policy-based methods, we directly learn to approximate pi without having to learn a value function. The idea is to parameterize the policy directly. So as we can see here, the inputs of this neural network would be all the states, or like the current state you are in. And then the output of the neural network should be a probability distribution of the actions. And after we get this probability distribution of actions, we can choose our actions randomly based on the probability distribution. And the larger the value, the more likely we are going to choose that action. So overall, this is a stochastic policy, which has many benefits compared to traditional Q learning, which will give you like a quasi-deterministic function for your actions. So one of the benefits we get is it avoids the problem of perceptual aliasing. So what is the problem of perceptual aliasing? It's basically the lack of information from the agent's observation of the environment. So there could be many states in the state space. However, it's most of the times the agents don't always have perfect information. So from their perspectives, for example, in this diagram, S1 and S3, although they are different states, S1 and S2, although they are different states, sometimes from the agent's perspective, they will get the same observation. So in this situation, there is no way that they can tell which state they are in, and if they act deterministically, it's possible that the outcome will be very bad. So like one real life example is in poker, you want to randomize your strategy even in the same situation. So, and because you don't have the full observation of the full information of everyone's state, sometimes it's better to act somewhat randomly so that you can achieve a better outcome. So now we are gonna go into a more concrete example. So in this game, this our agent is this cleaning robot. So it's trying to get suck the dust from this corner between two walls, and it doesn't want to like it doesn't want to do anything to the hamsters. However, because this cleaning robot is not smart enough, what it can observe is only whether it's next to a wall. So as a result, in both of the pink regions, it will observe that there's a wall in front of it, and that's all the information that you can know. So as a result, under a deterministic policy, the policy will either move right when in a pink state or move left. So either case, there's a possibility that our agent will get stuck and never suck the dust. So for example, if the agent starts from this state, and then the policy tells it that whenever you see a wall above you, you should move to the right. And then as a result, it moves to the right and see the hamsters. And then now it can only move to the left. However, because it's told to move to the right, every time in this state, it will just be stuck here, and it will never get to this the dust. However, if we have an optimal stochastic policy, which tells the agent to move left or right with 0.5 probability under the pink state, then it will not get stuck. And there's a high chance that it will get to this square no matter what state it starts with. So that's the benefit of a stochastic policy. Now we are going to introduce a very popularly used model, which is called PPO. So PPO stands for PPO stands for proximal policy optimization. And so the basic idea of it is to avoid taking bad actions that collapse all the training performance. So as we can see in this picture, assuming that we are climbing a hill. So basically, this is process of gradient ascent. So what we want is to gradually find our way to the global maxima where we maximize our reward. So however, if we use the traditional gradient ascent, we always choose the direction that maximize our reward, and also the step size that we take is proportional to how much improvement that direction could potentially benefit us based on the previous round's performance. And so it's like the loss function, except the constant we are increasing the value instead of decreasing the value. However, the problem of this method is that if you step a very large step, it's very possible that the the algorithm is not going to be very stable, and there's a possibility that you're going to step out the very steep cliff, and then you'll just go downhill and you'll never come back, and the model will not converge. So that's why we need to control the actions we make and the change. So the problem comes from the step size. So when the step size is too small, the training process will be too slow. However, if it's too high, then there will be too much variability in the training. So here with PPO, the idea is to constrain our policy update with a new objective function called the clipped surrogate objective function that will constrain the policy change in a small range using a clip. So this is the normal policy objective function. So it takes the log probability of taking that action at that state, and then times the advantage of the current state current action compared to the old action. So if we take a gradient ascent step on this function, we will like maximize our expected return, and gradually we'll get to higher and higher rewards ideally. So with the improvement from PPO, we can make this algorithm more stable by adding the clip function. So first of all, there are two main parts of this function. The first part involves a ratio function times the advantage. And the second part is a clipped gradient times the advantage. So we calculate the ratio in this way. The ratio is the probability of taking action AT at state ST in the current policy divided by the previous one. So as we can see, this ratio denotes the probability ratio between the current and old policy. If the ratio is bigger than 1, then the action AT at state ST is more likely in the current policy than the old policy. And if the ratio is between 0 and 1, then the action is less likely for the current policy than for the old one. So this probability ratio is an easy way to estimate the divergence between old and current policy. And on the other hand, so on the other hand, we will we want to take the minimum value of this ratio times advantage and the clipped result of clipped ratio and the advantage, because without such a constraint, if the action taken is much more probable in our current policy than in our formal policy, then this would lead to a significant policy gradient step. And therefore, it could lead to an excessive policy update. And so it's more likely we will fall down the cliff. So now it comes to the clipped part of the surrogate objective function. So this picture is like a good visualizer of how we clip the gradient. So basically, above 1 plus delta will no longer increase the gradient. And similarly, below 1 minus delta will no longer decrease it. So by clipping the ratio, we ensure that we do not have a too large policy update because the current policy can't be too different from the older one. So with the clipped surrogate objective function, we have two probability ratios, one non-clipped and one clipped, in the range between 1 minus delta to 1 plus delta. And epsilon is a hyperparameter that helps us to define this clip range. And in the original paper, epsilon was 0.2. And then we take the minimum of the clipped and non-clipped objective. So the final objective is a lower bound, which is like a pessimistic bound of the unclipped objective. And taking the minimum of the clipped and unclipped objectives means that we'll select either the clipped or non-clipped objective based on the ratio and the advantage situation. So here are some interesting open source libraries that you guys can explore. So Gymnasium is a newer version of the famous OpenAI Gym, and CleanRL is an environment for people to experiment, and also they have very good baseline reference. And Petting Zoo is a multi-agent version for reinforcement learning environments. So there are like multi-agent Atari environments. And Farama Foundation has a collection of even more games. So now it's game time. So all those games, as you can see here, can be trained using deep reinforcement learning techniques. And the training is usually very fast because the games are pretty simple and there aren't too many states. So I highly suggest that everyone, if you guys have free time, to look at the website and download some sample games to try out different reinforcement learning algorithms and see how they perform and compete against each other. And now we will do a demo of this game over here, which is called Slime Volley Gym. So okay. So now I'll start a game so that you guys can see how to play this game. So we can see a yellow agent and a blue agent, and I'm trying to control this yellow agent. So if the ball falls onto my side, then I lose a point. This is like kind of hard to play. And yeah, so I think I'm gonna lose to this blue guy very quickly. Okay, so it shows that I'm not a super skilled player for this game. However, now we want to, so feeling defeated now I'm gonna train a model to compete against that agent. So here is the script. Now we are gonna import PPO from stable baseline theory, which consists of a set of common reinforcement learning algorithm, and also I'm trying to train so this is a multi-agent game. So I'm trying to train it's difficult for like just one slime volley to be good at this game if it's training alone. So I'm gonna train two agents together by making them play against themselves. So here we define the environment, and here is the callback function. So in the callback, you'll save the best model if have sling. And then in rollout is basically where the agent learns. So it will choose the actions and states based on current policies and the observations. And then the environment will get updated based on the actions taken. And then based on the results, we will update our total reward. And here is the training loop. So in using a stable baseline model, we could just simply define our model as PPO MLP policy. And we could also change this to CNN policy to experiment with other possibilities. Or you could also choose non-PPO policies from the baseline model. So now I'm gonna run the script to train. Okay, so this is the trained model after like 10,000 100,000 time steps. So we can see that by training to play against themselves, the slime volleys become pretty good at maintaining and the ball is in the air, much better than me. Okay, so that's all for today's recitation. Wish everyone good luck for finals and the project. See you.